So today we will start with the next chapter in physics, which is mechanical waves or wave mechanics, right? This is directly a continuation of simple harmonic motion. So this is quite a significant chapter, or rather a significant section of physics in terms of the weightage in NEET as well as at the board level. So let's begin. You have some doubts from simple harmonic motion?
The last class you said that you will take some of the questions for practice of type of thing.
Okay. Any doubts from the major test pending?
So the doubts have been cleared by Sachin Pandey.
Okay. 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 So we'll discuss some additional questions in simple harmonic motion first. So we had discussed about compound or physical pendulum last time. So let's start with a couple of examples based on that. We had seen that the formula for time period where the pendulum is a rigid body suspended from a point like this, its center of mass being here, then d is the distance PC, where P is the hinge or the axis of rotation, and C is of course center of mass, and I is the moment of inertia about the point P. So let's begin with an example based on the calculation of this time period and the formula. Let's say we have a pendulum which is shaped like this, hinged at this point P. So this length is 2L, this length is L. So the inverted T shape pendulum is made of a material of uniform density and uniform cross-sectional area. We want to find its time period for small angular oscillations. So as we discussed, physical pendulum performs angular harmonic motion for small angular oscillations only, or small angular displacement or amplitude only. So that condition becomes a necessary thing for the angular harmonic motion. So we just have to apply the above formula, but in that we have to substitute the distance d of the center of mass and I, the moment of inertia about the point P. So just try this out. So first thing, try to locate the center of mass with respect to the point P. And secondly, try to write the moment of inertia about the axis at P for this rigid body.
Done, sir.
Okay, so let's check out the answer. So first thing, to find the center of mass of this given system, we can use a sort of superposition method. You can treat, since this is a rod of length 2L, you can treat its mass as 2m, let's say, where m by L is the mass per unit length, that material. Okay, so this is, let's say, rod 1. So its center of mass is here at a distance L, and the second rod of length L and therefore mass m. So this is rod 2, its center of mass is located here. So now when you place, or when you attach both these rods together, like this, let's say. Okay. So this one's center of mass is here. This one's center of mass is here. So the system center of mass will be somewhere here. Somewhere here. Such that with respect to this point P, we want to find this position of the center of mass. We use this kind of principle here. So 2m into L plus m into 2L. That becomes the idea. Okay. So you can see that this is 2 plus 2, 4 in the numerator and 3 in the denominator. So 4 by 3L. That becomes our YCM. So that is our distance D in that formula. Now the second thing is the moment of inertia, okay, about the point P. So moment of inertia about the point P is moment of inertia of rod 1, okay, plus moment of inertia of rod 2. So rod 1 is of mass 2m, length 2L, and the point P is one end of it. And the rod 2 is of mass m and length L, but this is ICM. Plus ml square. That kind of formula, parallel axis theorem. So this becomes 8 by 3 ml square for this one, plus 13 by 12 ml square for this one. So 32 plus 13, 45 by 12. Yeah. So this, I think, is the moment of inertia. So now our formula for time period. Now m is the total mass, remember. So here it will be 3m. this formula, m is the mass of the rigid body. So here it is 3m. Okay, so just go through the calculation carefully once. Oh, there is one, wait, there is one error here. This is not L, this is 2L. Wait, we'll have to make a correction here. Okay, Aruja, I'll explain the whole moment of inertia part in detail. So moment of inertia of a thin rod about one end, but this rod is of mass 2m and length 2l. So moment of inertia of rod 1 about the point P. This is a direct formula. You know that moment of inertia of a thin rod about one end is ml square by 3, whereas about its center of mass is ml square by 12. These are standard formula you have to know. Okay. So just applying that over here. That's how this term comes. Okay. Now the second term comes by parallel axis theorem. So rod 2, the point P is over here, is at a distance of 2L from the center of mass. So IP is equal to IC plus M into 2L whole square. So that's for the second rod. Okay, so go over the calculation of both these things carefully, then we'll look at the formula of time period. Hope it is clear now, Arujan. Let me know in case of any doubt.
Sir, it will be 81.
24 plus, oh sorry, 32 plus 49, yes, 81. So ultimately this will become how much? 81 by 12. So that is the thing, same thing as 27 by 4. Okay, so now you have this D and you have this. So remember here M is the total mass. So in this case, M should be equal to 3M. B should be equal to 4L by 3. And I should be equal to, okay. So substitute all this, you'll get the time period.
And sir, it will be I by mgd.
Hmm? Yeah.
I upon
Omega square is mgd divided by I. So time period is 2 pi by omega. So this term is to be inverted. Finally, this will become 27 L by 16G. So that is the same thing as 3 pi by 2 root L by 3L by G. And finally, this should be the correct answer, just verified. Okay, so this question is done. Is it clear?
Yes.
Let's look at an example of a spring mass system. Those are also very important. The most common type of questions are spring mass system based examples. So we have a smooth inclined plane with an angle of inclination 37 degrees. Now, combination of two springs like this attached to a block. K1 is 6 newtons per centimeter and K2 is 12 newtons per centimeter. And the mass of the block is, say, 1 kg. Take G as 10 meters per second square and take sine 37 as 3 by 5. So all this information is given. So now, first of all, find the time period for the blocks SHM. Secondly, if the block is initially pulled down from equilibrium by displacement of 1 centimeter and released from rest, find the amplitude, maximum speed, and maximum acceleration during its SHM. And also find the maximum and minimum extension of each spring for the case that we have in example in problem 2, part 2 of the question. So just try this out, people will discuss. So start with the time period. So you know how to do that. Reduce it to a single spring system, okay, and find the SHM time period from the standard formula for spring mass system. Then for the second part, you will have to first understand what is the equilibrium position. And from there, the initial displacement is given and all that. Yes, Varun, answer is correct for time period. So the first step, see, you can take a series combination. So in SI unit, it will become like this. Okay. Now you can see that for this system, time period will be 2 pi under root m upon equivalent k. So that will become this. You should just understand as a direct formula. However, can also be derived in this way, that understand that first of all, you reduce this to a single spring system. So if the single spring system at equilibrium, where the acceleration is 0, it has an extension of x equilibrium, let's say like this. Okay. So at this point of time, mg sine theta is getting balanced by this. Okay. And mg cos theta is getting balanced by normal reaction. So you have this is the mean position. Now from the mean position, if you take the mean position as s equal to 0. So if you displace the block further down by s, okay, so now your spring is having a larger extension where x is becoming xc plus s. So spring force will dominate over mg sine theta and have an upward acceleration. So E, which is minus d2s by dt square, will be such that so here x is xc plus s. So when you substitute this here, you get the relation that d2s by dt square is minus k by m s. So this is SHM with omega square equal to k by m. So time period becomes this. Okay. Yes. Varun, amplitude is correct, but for maximum speed and maximum acceleration, just use the SHM formula, na? A omega and A omega square. Yes, it's correct. Good. This is time period and omega is 20 radians per second. Okay. So now here you can see that this equation means that the SHM displacement where omega we've already seen is 20 radians per second, but amplitude will come from this formula. So initially at t equal to 0, we are giving it a displacement 1 centimeter below the equilibrium point and releasing it from rest. So that's how we can see that the amplitude will be equal to 1 centimeter. And the phase constant in this case will come out to be pi by 2. So our equation of SHM will actually be like this. Where E is 1 centimeter and omega is 20 radians per second. Therefore, for the spring X, okay, now this equilibrium value of X is given by mg sine theta by k. So that is 1 into 10 into 3 by 5 divided by 4 in Newton per centimeter. So you can see it is 1.5 centimeters. So X for the equivalent spring is 1.5 plus cos 20t in centimeters. So from this you can see that the maximum value of X is 2.5 centimeters and minimum value of X is 1.5 minus 1, that is 0.5 centimeters. Okay. However, this is not the answer to the third part. Okay. This is only the equivalent springs maximum extension and minimum extension. It's not why, it is how, right? Okay. That comes from this only, na? That S naught is given as, okay. So you can see that from this equation, this is A sine phi and this is A cos phi. So cos phi is 0 and sine phi is positive. So phi is phi by 2. You know the formula that phi is okay. So this is only the maximum and minimum extension of the equivalent spring. Okay, this is maximum and minimum extension of the equivalent spring, which has a constant k. But from this, we have to find the maximum and minimum extension of the individual springs k1 and k2. Okay. So the question is still to be completed for that third part. However, this will help us find the answer of the third part. From this itself, we'll find for the individual springs. Okay, so now let's understand this part. Yes, from this, how we want to find the maximum and minimum extension of each individual spring.
So can you explain the last step that
Which this one, this how we got the
yes.
value of x. Okay, so
No,
see
no.
that
On
is
X
related.
max and
That's simple, na? देखो 1.5 plus cos 20t term है ना. So cos 20t is maxima is how much? 1, na? And minima is -1, na? See, this is 2.5 centimeters plus a cos omega t, na? Now this term a cos omega t, it has a maximum value of how much? It ranges between plus a to minus a, na? Understood, na?
yes.
Because cos omega t ranges between +1 and -1. So this whole term, its maximum value is when this is +1, and its minimum value is when this is -1. So that's how it's 1.5 plus 1 is the maxima, and 1.5 minus 1 is the minimum. Okay, so this is clear, no?
Yes.
Okay. So let's also look at this visually once. Okay, so if you think of the oscillating system, so suppose this is the mean position. So this is where acceleration is 0, speed is maximum. Okay, I have to discuss the maximum speed and maximum acceleration also. I'm coming to that. Okay, could be going in either direction. So this is our s equal to 0 position, but this is where x is equal to xe, or 2.5 centimeters. Okay, so above this somewhere here, at a
It is
distance of 1 amplitude, okay, will be our extreme position where this acceleration will be maximum and v will be 0. Okay, so here and below this at 1 amplitude will be again the lowest position where acceleration is maximum in this direction and v is 0. So this is the extreme position. This is extreme position. So at this position, s is equal to plus a, because we are taking s in this direction, and x is equal to the maximum value, which is xe plus a. Okay, so this is 2.5 centimeters. Okay. Whereas this is where s is equal to minus a, so x is equal to xe minus a. So this is the minimum value of x. So like this. Now you can also see here that V max is equal to a omega. So 1 centimeter into 20 radians per second. So maximum speed the block will have at any point of time is 20 centimeters per second or 0.2 meters per second. And maximum acceleration is E omega square. So 1 centimeter into 20 square in radians per second whole square. So that is 400 centimeters per second square or 4 meters per second square. Okay. Later we can justify this by FBD also. If you look at the FBD at this position, you can see that so FBD method is giving you the same thing as your, okay. Anyhow, so more important than this is that at any point of time, if your equivalent spring is at an extension of x, then actually your combination of springs would individually be this was K1 and this was K2. So this is now at L1 plus X1 and this is at L2 plus X2. Okay. So you can see that for any extension of the spring, X is equal to X1 plus X2. Okay. And looking at the free body diagram of this point where they are connected, it's a massless point. So net force must be 0. So K1 X1 must be equal to K2 X2. Or from this you can see that X1 is to X2 is K2 is to K1. Okay. So combining this equation plus this one, you can see that X1 at any point of time will be K2 upon K1 plus K2 into X, and X2 at any point of time be like this. Okay. So now original system, let me see if I have taken them in same order. Yeah, K1, K2 are 6 and 12. And they're like this. Okay. So in our system over there, X1 is to X2 is 2 is to 1. So X1 will be 2/3 of X. X2 will be 1/3 of X. So X1's maximum value will be 2/3 of X's maximum value. So 2/3 of 2.5. And X1's minimum value will be again 2/3 of X's minimum value. Similarly, X2's maximum value will be 1/3 of X's maximum. And X2's minimum value correspondingly will be So this and this are the minimum values of x1 and x2, and correspondingly this and this are the maximum values. So this is the maximum difficulty level that you can expect for any spring mass system type of question.
Done, sir.
Okay, so hope these are clear. Let's move on to another question then. So we have a spring of constant K attached to a massless pulley here. This is another smooth fixed pulley. This is attached to a block, mass M. This is of course a light thread. So first of all, given that the spring constant is 12 Newton per centimeter and the mass of the block is 2 kg, G is 10 meters per second square. Find the extension of the spring in the equilibrium position. Secondly, if the block is released from rest at a position such that the spring is relaxed and the thread is taut, find the amplitude and time period of the block's SHM, and also find the maximum extension of the spring. So this is a problem where you will have to involve a bit of constraint relation concept that you've seen in Newton's laws type problems earlier. You can understand here that the extension of the spring will not be the same as the displacement of the block. There will be a constraint relation between them. Okay, so first of all, let's understand that whatever the tension in the thread, double of that is the spring force. This is having an extension x at some point of time, then 2t is equal to kx. Okay, so for equilibrium, let's say so extension of the spring at equilibrium is so that is 40 newtons divided by 12. This is the answer to the first part. Okay. Now the block is released from rest from the initial position where the spring is in relaxed state. So first of all, let's understand that at some point of time, let's say this was the equilibrium position. So we'll take this as a zero displacement position. Now from here, let us say the spring has got like this. So the block has this is now L plus X, where X is XC plus. You can see that if this makes a displacement of S, then this displacement here will be S by 2. So at this new position, I have an acceleration like this. So we have this is the second equation. Okay, whereas the first equation was this, that okay, in this equation there is a mg term. So include that. This is our second equation. Now you incorporate this over here. So kxc by 2 and mg term cancel out. So we have ks by 4 is equal to ma, and a is minus d2s by dt square. So we can see we've got our SHM equation. Like this. So omega square is k by 4m. So time period of the SHM is this. So let's substitute the values now. So the spring constant was 12 newtons per centimeter and m was 2 kg. This is our time period. So just go through this section once, then we'll discuss about the equation of SHM. Okay, now the next thing is that initially x is equal to 0. This is at natural length. So if you compare this with the mean position, or equilibrium position, so you can see that this displacement is 2 times x. Okay. So from here, you can see that with proper sign, we'll write it as minus 2x because we are taking the downward direction as our s-axis. Okay. So s is equal to some amplitude. It's okay. Where now at t equal to 0, s naught is minus 2x. That is minus, and v naught is 0. So this is how we are releasing it at t equal to 0. So amplitude and the phase constant will be minus pi by 2 because here s naught is negative and v naught is 0. So the equation of SHM will become like this. Okay. Now you can see that x at any point of time, this, okay. So x's maximum value is xc plus amplitude. So this will be the maximum extension of this plane. Okay, so with this, we complete this additional practice problem exercise. Okay. So please complete maximum problems of SHM from your exercise 1 of the module or any other practice book you're using for NEET level questions. And next time we will start with mechanical waves or wave mechanics. Okay, that's it for today's session.
Sir,
Wish you all the best. Yes,
in the previous question,
yes,
the inclined,
yes.
in case that there were two springs attached on the opposite ends of the block. So will
That
that
would
be a parallel combination?
that will be a parallel combination, but then you'll have to have an arrangement like this, where there is one wall here, one wall here. Understood, no?
And if the both spring constants are same, then also it will be parallel.
See, same or different, that doesn't matter. That the important thing is here, if the block is pushed by X, okay, then what is happening? This spring will also push with a force K1X, and this spring will also pull with a force K2X. No? So the net force is becoming how much? It is becoming K1 plus K2X. No? So it's a parallel
Yes.
combination. Okay. So it could be like this, or it could be like this also. Even this would be a parallel combination. So these would be the examples of parallel combination. In these two kind of situations, your equivalent K would be K1 plus K2. Whereas in this situation that we've seen in this particular problem, it was series combination. Okay. Hope the point is clear.
Yes, sir.
Okay. Okay, so that's it for today's session, people. Thanks for attending. Wish you all the best. Have a nice day.
Bye. Thank you.